Okay, now before I go ahead and discuss the buckling problem, I want to solve some example from your book using Heaviside function, and then you can compare the solution in the book, and then you can see how significant amount of simplification is done if you use Heaviside function. So let's go ahead to page. Let's write here page 730, and this example 16.4 up. Of course, it's the 5th edition book, but for you guys that don't have the book, I can just write it here. This problem is you have a beam, and now the supports are a little bit more complicated. Here you have a pin here, and then you have a roller right here, and you have point load 4K at one end, and these distances are given. This is a different color here. It's 2 from here to here, and it's 1 from here to the end, and 2 1 4K, and what it's asking for, it says the beam is subject to a load at point C, determine the displacement at C. So if this is ABC, it actually is asking for deflection at point C. So let me, before I solve using Heaviside function, let me draw a qualitative form of the deflected neutral axis. So you're going to get something like that. You see that? And then that's your deflection, or V, at point C. So it's going to go down, as you can see. Now, before I actually solve this, I know that my EI, product of EI, I usually used to take this as 1, but in this example it just simply say take it as a constant. That means the final result should be a function of E dot I. Okay, so let me just go ahead and set up the problem. The first thing we do, we find the reactions. So this is your beam, you draw a FD, you're gonna get unknown BY, AX 0, but I just put it here AY, no moment at A, Y, because the A is just simply a pin, right? Both A and B, so there is no moment here. And then you're gonna get a 4K right here. So I just go ahead and write moment equation about point A is 0. That's going to give me By times 2 negative 4 times 3 is equal to 0. The other equation, I write summation of moment about B. I could just simply say summation of force in y direction 0. So the second equation will give me 4 times 1. When I say 4, it's actually 4K. Don't forget this K here. So 4K times 1, negative. And then you get negative AY times 2 is equal to 0. So if I solve the first equation for BY, my BY is equal to 6K positive. And the second equation directly give me AY. So 2AY is equal to negative 4K. So that means AY is negative 2K. So once I get my reactions, I just put it right here. So BY is 6K, and AY goes the other way. Let's erase this direction. and so this is your beam. So AY is going to go the other way, and its value is equal to 2K, positive the other direction. So if you take it upward, originally I took it upward and I solve it, get negative 2K. So I just flip the sign and it's now positive 2K. So this is all I get for the reactions, and AX is 0 obviously. So I didn't put it there. Now I'm ready to go ahead and cut from left to right and apply Heaviside function. So I take my reference again from the left and I try to cut it just before the very end to include all the loads X, and now my system is the one on the left. You don't do anything with the part on the right. That's the right system, right? So you don't do anything with the 4K. So if I draw FVD for that, I get this one. So you have a 2K here, then you have 6K here, then you have M of X, and then shear load V at X, and everything else is just distances that I'm going to include them. So from here to here is X, from here to here is 2, and from to here I simply don't know. Okay, so now I say I'll just write one single equation to get my moment at X. What is that particular equation? That equation is summation of moment about point X is 0 in this system. So you're gonna get mx positive, and the next thing is negative 6K times heavy side X minus 2 plus 2K times X is equal to 0. Then you solve for mx, so your moment diagram is just one line equation. 6K times X minus 2 negative 2K times X. So please compare this simple solution with the mess in your book. The way your book solve it, it takes a lot of equation. So you have 2 different intervals, so you have 4 constant of integration plus 2 from the support, so you have 6 constant of integration. So it's a lot harder than just simply applying Heaviside function. So now I'm just ready to just plug this into the integration equation and get the deflection. So the V double dot, or simply this is the second derivative of V with respect to X, right? So I simply use V double dot. So I have V double dot is equal to mx over EI. Because according to the assumption of the equation, EI is constant, you can just take this to the left and just keep it on the left. So you have EI times V double dot is M of X. Let's plug M of X from the above. So you have 6K times heavy side X minus 2 minus 2K times X. So let's go ahead and take the first integral. I want to show it with a different color. So let's take integral of both sides, and then I will get one constant of integration. So if I do that, I get EI times V dot from the left is equal to 6K heavy side X minus 2 over 2 minus 2K X2 over 2 plus C1. I simply took the integral of this term, which result to EI V dot, and for the right side, so you get 6K heavy side X minus 2 to the 2, the second power divided by 2, minus 2K times X2 over 2 plus C1. Now you can see that because I don't have any information about the slopes, you see, if you look at here, I don't really know the slope of curve at point A. This is theta, or a slope at point A, or dV dx at point x is equal to 0. They are all identical. I do not have this information. And similarly, I don't have the slope at point B. This is theta at point B. So that means I cannot impose anything on the derivative here. Look at here, I have v dot, it's not v. You see this term? So I'll just go ahead and take one more integral before I'm able to apply the boundary condition. So one integral here. So let's do that. If I take that integral, then I'm going to get EI times V of x is equal to, so you get 6k over 2. You already had that. So you say heavy side x minus 2 to 3 over 3 minus, there is only 1k here. So you say x3 over 3 plus the integral of c1, because it's constant, is c1 times x. Then you get another constant of integration c2. That's all you get. Okay? So now I'm ready to apply boundary conditions. Before I do that, let's simplify this a little bit further. 6k divided by 3, so I eliminate 3 here. And then 6 divided by 3 is 2k. And 2k divided by 2 is 1k. So the entire coefficient of this term is simply 1k. Okay? So now boundary conditions are v at x is equal to 0 is 0. That means deflection at point A, look at here, point A is simply x0 is 0. And also the second boundary condition is v at point B, which is 2. V at point x is equal to 2. This is point A, above. The bottom is point B. Is equal to 0. So I have these two constants, two conditions. So let's apply them. If I put x0, what do I get? I get EI. Put x0 here. V at x0, which is simply 0, is equal to, if you put x0 here, you get 0. The second term is 0. The third term is 0. And finally, you get C2. Okay? So all of them is 0 except C2. And that means C2 is equal to 0. Now let's go ahead and apply the second conditions. The second boundary condition is, say, the deflection at point 2 is equal to 0. So let's put x is equal to 2. Again, you get EI times 0, which is 0 on the left. And then if you put x0, the first term right here disappears because we put x2, right? But the second term is right there. So we have 1k over 3. And then 2 to the 3 is 8 times 8 plus c1 times 2 plus c2, which is basically 0, is equal to 0. This is my second equation. So I can solve this equation directly for C1 because C2 is 0. So what do I get? I get 2C1 is equal to positive 8K divided by 3. Divide by 2 both sides. So you get C1 is equal to 4K over 3. So that's what you get. So let's put it back in the equation. If I put it back in the equation, my equation is, I'm talking about, let's highlight it, the equation of the deflected neutral axis. This equation, let's highlight it. This is my main equation. Now I have both C1 and C2, so I can uniquely explain or show the deflection of neutral axis. So I get V at any x, the deflection at any x, is equal to 1 over EI times 1k heavy side x minus 2 to 3 minus 1k divided by 3 x to the 3 plus C1, which is 4k over 3 x plus C2. And what is C2? 0. So that's it. That's my final relation. Let's put it in the box that I use to compute the deflection at any point x across the beam. So the question that the question in this problem is to find, let's go back to the main question, to find delta at point C, or deflection at point C. So what is the location of point C? Well, the point C, x of point C is equal to 3 from left to right. So all I need to do is to put x is equal to 3 into this equation. So let's do that. V, the deflection of point C, or V of C, is equal to V at x is equal to 3, which is equal to, if you put 3 here, you get 1 over E, 1k times 3 minus 2. Look, 3 is greater than 2, so you treat Heaviside like parentheses. So it becomes Heaviside x minus 2 become parentheses x minus 2 to the third power. But what is x minus 2? X is 3 minus 2, 1 to the third power is 1. So still you get 1. Okay? The second one, negative 1k over 3 times, put 3 here. So 3 to the third power plus 4k over 3 times 3. So let's simplify that. So you get 1 over EI times 1k minus, this becomes 27k over 3 plus, this becomes 4k, which is basically, I can write it like 12k over 3. So 1k, negative 27k divided by 3 plus 12k divided by 3. And this 1k, I can write it 3k over 3 instead of 1k. You see that? I can write it 3k over 3. So now I have the same denominator, so I can simplify that. 1 over EI, 3 minus 27, it becomes a negative 24, and plus 12 is negative 12. So top I get negative 12k divided by 3. Negative 12 divided by 3 is negative 4k over EI. So the answer to this question is deflection at point C is negative 4k over EI. And you know that this thing can be done in couple of lines. If you practice, the first thing you do, you can directly go, let's use a different highlighter, like pink. You can directly go ahead and find, first of all, these are easy, they're support reaction. You have done it in vector statics. So the first thing you do, you can directly go ahead and find this relation in just one line. If you practice, you can do it in one line. It's going to take you 60 seconds, trust me. And then if you double integrate and apply boundary condition, then you get this line. So let's say this also, you do some computation here. So 1 line, 2, and then 3. In 3 lines, you're going to be able to get the final solution, which is negative 4k over EI. And that's exactly what you get in your book. But the one in your book, you have to solve for several constants of integration, 4 constants of integration, if you do the method in the book. And that's going to take you a while. The book does it in 2 pages, but if you do it on paper yourself, I actually recommend that you do that. Go ahead and do it. You're going to do it in at least 4 or 5 pages. So this is one example. I actually have some example from my previous videos, in the previous lectures, in the previous classes. I'm going to find it out and post the link for you so you can practice for your final exam. And now let's go and talk about buckling. So back to the topic that if you had a column like that, and we have some axial load, which is compression, let's say P, and let's say the length of this object is L, we know that, well, in some extent, this is going to compress in the like linear elastic behavior. But after some particular point, this is going to start to buckle. That means this is going to go like a bow-shaped profile. And in this case, the equation of, when we do F over A is equal to E delta L over L, this is no longer valid after it buckles. So now the question is, well, if this is my design equation that I use to do a lot of things, I want to know when this equation is valid. Well, we already discussed it. This is only valid in proportional region or linear elastic region. And you know that. That means that if you draw the stress in this object versus epsilon, the strain, you get some curve like that, and then it goes like this, and then you have failure. It's only valid in this region. And you know that before. Another limit for that is only valid before it buckles. Before it buckles. Because after it buckles, then you get a lot of deflection for no additional force. So now the question is, what is the P that causes buckling? Now, in order to answer this question, you have to do some sort of what they call it eigenvalue analysis. And the level of this analysis, if you want to do it correctly, is above the limit of undergraduate mechanics of material. You have to learn graduate course in eigen decomposition, and you have to understand the eigen mode of ordinary differential equation, and then you have to go through a lot of things as your book is trying to make it accessible for you, right? So the end result, the final equation that you get for this P that causes buckling, we call it P critical. Critical, that means it's the point that buckling just happens. The final equation you get is a simple equation in the term of module of elasticity, the length of the beam, and a constant of that depends on the support type. So let's say this beam is fixed to this point A with some support, is either fixed like that or pinned. Either fixed or pinned like that. And also it's either fixed to point B on the top or pinned. So we have different, so for each one of these different boundary conditions, we have different P critical. So in order to include all of them in one equation, you can write P critical is equal to pi square EI over KL square. That's the equation you get for the deflection of a cylinder. You see your beam column, well, I'll call this beam, but in fact it's a column, should be cylinder. That means your length over diameter should be a very large value, such that this equation is valid. But if you do all this analysis, eigenvalue decomposition, and finding eigenmode of ordinary differential equation, then you get P critical is equal to pi square EI over KL square. In fact, that's the equation in equation number 17-11 in page 787. So how can we use this equation? Well, depending on different type of boundary condition. For example, if I only have pin, then my K is simply, you see this K, this constant is responsible to handle different boundary conditions, different BCs, boundary conditions. Okay, so if I have, for example, if my column is supported by 2 pin at point A and B, like that, then this K is 1. But if it's supported by fix or pin fix, then your K is, so let's write it here, your K in this equation is either 1, 0.7, 0.5, 3 different values. 1, if both A and B, point A and B, are pinned. If both of them are pinned, then your constant K is simply 1. And if one of them is pinned and the other one is fixed, then you get 7. So either one pin or the other fixed, then you get 0.7. And if both of them are fixed, then you get 0.5. So this analysis is very simple. I want to show one example here. Let's say you have a kind of rectangular base for your column, like that, and then let's say this is 2, this is 4, and the length of the beam is, I do not have charge in my iPad, it's 7%. Hopefully I don't run out of charge, so I try to quickly finish this example. So your base is shown as a rectangle 2 by 4, and the length is like 8. And don't forget that if this is like centimeter, you have to convert it to meter. Okay, and the E is given 200. It is a Young module of elasticity, gigapascal, and this is pin. So you have one pin here, and there is another pin here, and these two pins, they actually move together. That means you have axial load on it. And then the question is, at what point it starts to buckle? Well, I use this equation that I just highlighted. So I say P critical is equal to pi squared times E 200 times 10 to 9 gigapascal times, well, for I, you have two axes. Let me show the axes, the two axes that we have here. One axis is like that, and one axis is like that. In this equation, you put the smaller one, because for the smaller one, the buckling happens around that axis, that the moment of inertia is smaller. So here, the smaller one, if I, for this rectangle AB, if I is 112 B times A cubed, right? So the smaller one is obviously this axis. So here you put, instead of I, in the equation, you put 112. So 4 times, and 4 you say 4 10 to negative 2 times the 2, the height, 2 to 10 to negative 2, 2, 3. You see, the smaller, you substitute the smaller moment of inertia. The other one, the other moment of inertia about this axis right here is equal to 112 2 10 to negative 2 times 4 10 to negative 2 to 3. This is obviously way larger than this one that I substitute in the formula, divided by K, which is in this case pin, so K is 1 times the length, the effective length of the beam. Here length, effective length between two support is 8. So you put 8, the entire thing square. So you put it in a calculator and you find the critical load. Before this critical load, all the analysis that we have for FA is equal to E delta L over L. You remember we computed the deflection. We did a lot of things with this equation before. This is all valid before buckling, as long as you are you are in the proportional, in the linear elastic region. If you are in this region and you are before the buckling, all your analysis is completely valid, very accurate. Otherwise, your computation is not valid. Okay, so let's finish up this thing before I lose the power. So I need to recharge the iPad and put more helpful videos for you.